Hi guys, welcome to my channel. In this video, we are going to start a new advanced data structure, that is skipList. So what all we are going to cover in this video? First of all, we will see that why do we need a skipList, or what advantage does skipList has over other data structures that we have learned until now, right? And then we will look at that what are skip list, or how does a skip list look like, the structure of the skip list, right? And then we will move to a perfect skip list, or when do you call a skip list as a perfect skip list? And then we will see that a perfect skip list is ideally not possible because of insert and delete operations. That is why we need to focus on something that is known as a randomized skip list, right? Then we will move to randomized skip list, and thereon we will see different operations like search, insert and delete operations in a skip list, right? And after that we will see different operations like search, insert and delete in case of a skip list. As skip list is a probabilistic data structure, so we will do probabilistic analysis in order to analyze the skip list in a greater depth, and we will this will involve a lot of proof and algebra, this probabilistic analysis. And then finally we will discuss the time and space complexity. We will do some kind of proof and computation over here as well. So we will also discuss a trade-off over here between time and space complexity when it comes to a skip list, right? So we will be discussing all these things, right? And as you can see, I'll be covering each and everything about this data structure, that is skip list. So in order to ensure that the length of the video is not very large, I'll be covering these 4 things in the first video, and the rest of the 2 things in which I'll be doing a more in-depth analysis of this data structure in the next video, right? So if you want to know that why do we need a skip list, what are skip lists, the structure of skip list, and what is a perfect skip list, and what is a randomized skip list, how do we perform different operations like insert, search and delete in a skip list using different examples, then watch this video. And then later on, if you also want an in-depth analysis of this data structure skip list, wherein you will see a probabilistic analysis and you will also compute the time and space complexity with me, for that you need to watch the next video. So in these 2 videos we will be covering each and everything about skip list. So let us start. So why do we need a skip list? So suppose you have got a sorted array, okay? Like let us just take an example that we have got this sorted array, okay? So what is the time complexity of searching an element in this sorted array? So you will say, if you have learned binary search, that because this array is sorted, so the time complexity for the search operation will be order of log n, right? For searching for any element in this sorted array. Now before talking about sorted linked list, just tell me that you are aware of this thing, that if you want to search any element in an unsorted linked list or in a normal linked list, the time complexity of that search operation will be order of n in the worst case, because it might happen that you have to traverse each and every element in an unsuccessful search of that linked list in order to determine that that element is not present in the linked list, right? So for an unsorted linked list, the time complexity of the search operation will be order of n. What about a sorted linked list? So let us take a sorted linked list. So suppose you have got this sorted linked list. So what will be the time complexity of the search operation in this sorted linked list? As you can see, 5, 10, 15, 20, 25, 30, 35, 40. All the elements are sorted in this linked list. So some of you might say that here also we can perform the binary search operation, where we will look at the middle element and then we will determine that if this middle element is less than that element that we are searching for. So if this middle element is greater than that element that we are searching for, so we will search in this area, right? That is what we do in a binary search. But the time complexity of binary search in case of a sorted linked list will not be order of log n. It will be order of n. Why? Because if you want to come at this middle element, you cannot randomly access this middle element as you could in case of a sorted array, right? Where random access is possible. If you know that the length of this array is n, you can go in order of 1 time to n by 2's index, right? You can go to this index in order of 1 time. But when it comes to a linked list, that is not possible. If you have to come to this n by 2th index, you actually need to travel all these nodes between 0th index and n by 2th index, right? You need to travel all these nodes. So in the same way, because random access is not possible in case of a linked list and you need to traverse in a particular order, or this is an ordered data structure, or you need to traverse one by one all the elements, so the time complexity of the search operation will be order of n in case of a sorted linked list, right? So now the question arises that can we reduce this time complexity of order of n? Can we do something about it? Now you might say that the best thing is that we store all these sorted elements in an array, right? And in that case, the search operations time complexity will be order of log n. So why don't we do that in order to reduce the time complexity of the search operation? But this is not a very good alternative. Why? Because in case of a sorted array, if we want to insert an element somewhere here in the middle, right? So if we want to insert 6 over here, so the time complexity of this insert operation or any kind of update operation will be order of n, right? That time complexity will be order of n if you want to insert an element. But if we are given a pointer over here already and we want to insert this element 6 over here in case of a sorted linked list, the time complexity will be just order of 1, or it will just involve changing some pointer here and there and your insert is done. If you are already provided a pointer to that position where you want to insert the element, right? If you are already provided a pointer to that relevant position, it will take constant amount of time in case of a sorted linked list. But here if you want to do any insert or delete operation, it will take you order of n time, right? So in those cases where you are doing as many updates, as many searches you are doing in your data structure, this is not a good alternative. A sorted array is not a good alternative. So you want something in which your insert and delete operations as well as your search operation takes lesser amount of time, right? So that is where skipList comes into the picture, where your time complexity for the search operation is reduced from order of n, and the insert and delete operations also take less than order of n time as they took in case of a sorted array. So that is where we need skipList, right? So now let us see what is a skipList. So what is a skipList? A skipList is a probabilistic data structure, right? And we will focus more later on upon this property, that it is a probabilistic data structure, but it is also having a hierarchy of sorted linked list. That means a skipList is basically having a structure in which there are multiple linked lists in a particular hierarchy, right? So earlier we talked about a sorted linked list, right? Not a skipList. And this sorted linked list looks something like this, right? So this was the sorted linked list that we saw earlier. When we talk about a skipList, we can have more than one sorted linked list, right? So if I draw another sorted linked list on top of this sorted linked list, so for time being, let us call this sorted linked list as L0, right? And now I will draw another sorted linked list on top of this linked list, that is L1, right? But I'll copy the elements of L0 itself in case of L1, but I'll not take all the elements. Instead, I'll take a subset of all these elements present in L0 in order to make a set of L1, right? So L1 will contain a subset of elements present in L0, right? And I can take them in this manner that I'll take all the alternate elements. That means I'll take 10, 20, 30 and 40, right? So let me take all the alternate elements in order to make my L1, right? So this will be, I'll take 10 over here, then I'll also take 20, I'll also be taking 30, and then I'll leave one element and I'll take another element, that is 40, right, for my L1. Okay, so all these elements will be connected like how they are connected in a sorted linked list, because this is again a sorted linked list, right? So this is my L1, that is a sorted linked list. And let us say by default each and every sorted linked list that we are going to draw will have a node initially that is going to be minus infinity, right? Or you can also call it as a head node, right? So each and every sorted linked list will have this node, right? And let us also say that there is also a tail node in case of each and every linked list, and this link, and because this is a sorted linked list, that node will be infinity, will have infinite value, right? Or in coding terms you can say it will have int max value, right? So we have got this. Now suppose I want another sorted linked list on top of this L1. I want another sorted linked list. So again, I'll be taking only alternate elements out of these 4 elements that are present in my L1, right? I'll just be taking only alternate elements. So I'll leave this first element 10 and I'll copy 20, right, for my L2. I'll also leave 30 and I'll take an alternate element, that is 40, right? And as you can see, I'm also drawing the top and down pointers. That means someone go from L1 to L2 and also come from L2 to L1 on the node with the same values, right? Like you can go from L0 to L1 to L2, and of course there are forward pointers each and everywhere. So this is also my sorted linked list. You will again have your tail node over here, that is infinity, and a head node that is minus infinity. Okay, so this is my L2. Now suppose I have got another linked list in which again I'll be taking only alternate elements out of my L2. Here in L2, as there are only 2 elements, 20 and 40, so I'll be leaving the first element and taking this second element, 40, right? And again I'm having a tail node over here, infinite, right? And a head node, right? So this is my L3, right? And now when you look at this, you will see that we are having multiple sorted linked lists. So L0 is a sorted linked list, L1 is a sorted linked list, L2 is a sorted linked list, and L3 is a sorted linked list, right? And this entire structure that you can see right in front of you is actually a skip list, right? So this what I've drawn over here is a skip list. We will analyze later on that why it is also called a probabilistic data structure, but I guess you have understood that a skip list is basically a hierarchy of sorted linked list, right? So as you can see, there are many sorted linked lists over here, and for each and every level it contains those nodes that are in the previous level, but it contains a subset of those nodes. Like over here, as you can see, there were 8 nodes. Here you will see these 4 nodes that are in L1 are actually a subset of these 8 nodes, right? And here also in case of L2, there are 2 nodes, but again these 2 nodes are actually a subset of these 4 nodes in L1, right? So here we have decided that we will only be taking the alternate elements in this linked list and copy them in the linked list that is above, right? Over here also we decided that we will be following this strategy. It is not necessary. we can also say that we will be leaving two nodes and then copying one node to the top linked list. Like suppose if we would have said that we would actually be copying 15 to L1 and leaving out 5 and 10, and then we would be copying 30 by leaving out 20 and 25. So here we would have actually left out two nodes and then copied the third node on the top linked list, right? And then we would be leaving out 35 and 40, and so this right, so only two nodes in that case, 15 and 30, would have been in L1. So but rather we decided that we will be taking all the alternate elements and copying them to the just above linked list, right? So in this strategy, over here if you see, in case of L0, you have got 8 nodes. In case of L1, 4 nodes. In case of L2, 2 nodes. And in case of L3, you have got 1 node, right? So basically, if you consider the total number of nodes in your bottom linked list as n, right? So here your n is equal to 8, right? So basically here you have got n number of nodes in your L0. Here you have got n by 2 number of nodes. Here n by 4 and here n by 8, right? So if I ask you the number of levels that you will have in any skip list that is following this strategy, that it will take only the alternate elements and copy them to the linked list that is just above, right? That we are doing over here. So if I ask you that approximately how many levels will be there in such a skip list in which the bottommost linked list has n nodes. So the number of levels in skip list. So number of levels in skip list. So as you can see, because in each and every linked list, the number of nodes are being half, then that is the linked list that is just below it. So here the number of nodes are being just half as we go upwards, right? So we will do this until and unless we are left with just one node. So if you determine the number of levels in such a skip list will approximately be equal to log n, right? Log n to the base 2. So the number of levels in such a skip list will approximately be equal to log n, right? So now earlier we saw that the time complexity of the search operation in a simple sorted linked list was actually order of n, right? But how do we do the search operation in this skip list? So suppose we want to search for 35, right? So suppose if we want to search for the node 35 in this skip list, we will start from the topmost linked list, that is L3, and we will start from the head of this linked list and we will see. So if the next element over here is actually having a greater value than this value that we are searching for, so we will move down, right? So we will come down in this case. So we will come to L2 because over here when we look at the next node, it is having value 40. So if we come over here, we cannot. So if we suppose we come at 40, then we don't have a way to go back to 35, right? So we will always ensure that the next node, if it is having a greater value than the value that we are searching for, so we go down, right? Again we look at this node. So is 20 having a greater value than 35? No. So in such a case, we can move forward, right? And we come on 20. Then again at 20, we look that the next node, is it having a greater value than 35? Yes, the next node is having value 40. So we cannot go at this node. If we go at this node, we will actually move ahead of that value that we are searching for, and we have no way of coming back, right, from 40 to 35. So we will not go there, instead we will go down, right? And again at L1 on this node 20, we will look at the next node. Is the value of 30 greater than 35? No, 30 is less than 35. So we move right and we come on 30, right? And then when we look at the next node, 40 is having value greater than 35. So we can't go right, so we will come down, right? And then we will come at 30 and we will look at the next node. Is 35 having a value greater than 35? No, 35 was the value that we were searching for. So we found 35 over here, right? So as you can see, this is how we do the search operation in such kind of a skip list, right? So over here, if you would have noticed, what we did was we started from the topmost linked list and then we moved down whenever we saw a value that was greater than that value that we are searching for, right? So wherever we found a value like 40 that was greater than the value that we are searching for, we moved down. Otherwise, we moved in the right direction. But again, if you have paid attention, you will see that at each and every level, we are at most comparing two nodes, right? We are not comparing more than two nodes. We are not comparing more than two nodes. Like over here, you saw that we just looked at 40 and compared it with 35, and then we moved down. So we just compared with one node. Here also we compared just with one node. Here we compared with 20 and 30, so two nodes, and here we compared with two nodes. So at each and every level, we are just comparing with two nodes, right? So if you talk about the time complexity for the search operation, so it is 2 into the number of levels, because we are comparing with just two nodes at each level. So the number of levels we have determined earlier in such kind of a skip list will be approximately log n. So the time complexity for the search operation in this skip list will actually be order of log n, right? So we saw that in a normal sorted linked list, like if we just remove all these top levels L1, L2 and L3, and just if we think about L0, and if we want to search an element in L0, it will take us order of n time, right? But when we talk about this entire skip list, and if we want to search an element in this entire skip list, it is just taking us order of log n time, right? So such kind of a skip list in which we actually promote only the alternate elements. So here we can call this as a promotion, that we are copying this node 10 to the top skip list. So actually we are doing a promotion. So here as you can see, we are actually promoting all the alternate elements. Even in this case, we are only promoting the alternate elements out of all the elements at a particular level to the top level, to the just top level, right? So such kind of a skip list in which we are promoting the alternate elements and the number of levels in the skip list is actually log n. So such kind of a skip list is known as a perfect skip list, right? Because we are actually following a pretty straightforward structure over here, that we are promoting only the alternate elements to the next level, and the number of levels in this skip list is approximately equal to order of log n, even in the worst case, right? So such kind of a skip list is actually known as a perfect skip list. So such kind of a skip list is known as a perfect skip list. But it is not always possible to actually maintain a perfect skip list like this, where you are ensuring that only the alternate elements or the alternate nodes are promoted to the next level. Only the alternate nodes like 20 and 40 over here are promoted to the next level, and 10 and 30 are not promoted. So we are actually following an alternating structure. So this thing is very difficult to maintain. So now you may ask, why is it very difficult to maintain such kind of structure? So suppose if I want to insert in this skip list another node with the value 27, right? So what I'll do, I'll actually first of all search for 27. So how do I search in a skip list? I'll start off from the topmost level, and then I'll see that is the next node greater than 27? Yes, it is. So I'll move down. So is the next node 20 greater than 27? No. So I'll move right. So now I'll come over here. So now I'm on 20, and I'll see, is 40 greater than 27? Yes. So I'll move down at this 20, right? And then I'll see, is 30 greater than 27? Yes. So I'll move down over here. And then I'll see, is 25 greater than 27? No. And then is 30 greater than 27? Yes, 30 is greater than 27. But then I'll try to move down But as this is the bottommost linked list, L0, so I cannot move down. So basically this is the position where I am actually going to insert 27, right? So my 27 is going to be inserted over here between 25 and 30. But now just understand, if I insert 27 over here, this alternating strategy that I followed, that of promoting only the alternate nodes in the top level, how will I follow this over here? So in order to follow that strategy, so basically 10 will go at the top level, 20 will also go at the top level, but 25 will not go and 27 will go at this top level. So basically 27 will be there on L1, but 30 will not be there, right? 30 will not be there in case of L1, and 35 will also go, because after 27 we are actually following the alternating strategy. So we will not take 30, we will not promote 30, but we will promote 35, right? We will promote 35, but we will not promote 40. So as you can see, so again there will be a change in case of L1, and again there will be a change in case of L2 in order to maintain a perfect skip list, or in order to ensure that only the alternate nodes are actually promoted on the next level, right? So this will actually require changing a lot of nodes, or almost all the nodes, in case of a skip list. So that is why we cannot follow the strategy of only promoting the alternate nodes at the next level or at the just top level. So this is one of the drawbacks of a perfect skip list. So that is when we move from a perfect skip list to a randomized skip list, right? So this problem that we are facing while inserting any node, or which we will also face when we delete a node from the skip list, in case of a perfect skip list, we are not going to face this problem if we talk about a randomized skip list, or if we make this skip list as a randomized skip list rather than following a very strict order of only promoting the alternate nodes as we do in case of a perfect skip list. So now let us see what is a randomized skip list and how do we perform different operations like search, insert and delete in case of this skip list, randomized skip list, that gives a better efficiency for almost all the operations and is more feasible as compared to a perfect skip list. So in case of a randomized skip list, again at the bottommost level or L0, we are having all the nodes, right? All the nodes that are present in the skip list are actually also present in the bottommost linked list or the bottommost level, and it is not necessary that we only take only the alternate nodes and promote them to the top linked list or the next level L1, right? We can also take this 15, right? And we can take any random nodes and let us promote them at the top level, right? And it is not necessary that here if there are n number of nodes in case of L0, so L1 should have n by 2 number of nodes. So now again here I can take random nodes. There need not be the alternate nodes to be promoted to L2. So this was my L1. Now let me draw L2. So I'll also promote 15 as well as 20 to L2, and let me also promote 30 and 35, right? Only 10 in L1 is not promoted to L2, right? So this is my L2, and let me promote this 15 and 35 to my L3, right? Okay, so here I have drawn L0, L1, L2 and L3. And as you can see, the structure over here is actually not that straightforward, because here I have promoted random elements to the next level, right? Here I have randomly chosen those elements. Like here 10, 15, 20 I have promoted, I have left out 20, then 30 and 35, and then left out 40. Right? Here as you can see, I have promoted all the elements from L1 to L2 except 10. Right? So I am actually following a randomized kind of structure. Right? That is why this is known as a randomized skip list. And as you can see, a very striking difference if you compare it with your perfect skip list is that in case of a randomized skip list, there is no particular structure. It is very random if you look at it, because we do not follow this strategy that every alternate node has to be promoted to the next level. Right here, I have randomly chosen 10, 15, and 20 to be promoted from L0 to L1, and 30 and 35. Similarly, I have followed this random strategy. That is why this is known as a randomized skip list. Now, how do we do a search operation in case of a randomized skip list? So, if I want to search for suppose 36 in this skip list, so the search operation in a randomized skip list is actually similar to the search operation in a perfect skip list. You need to follow the same steps. So you will start from the head of the topmost linked list, and you will see, is the next element greater than the value that I am searching for? Is 15 greater than 36? If it is greater than 36, then I cannot come over here. Otherwise, I will have to come back, which is not possible in case of a skip list because there are no backward pointers. So in this case, 15 is actually lesser than 36, so I can come here at the right. Okay. Then is 30 greater than 36? No. So I have no problem in coming at the right. Then is 35 greater than 36? No. So I can come here at the right. Then I look at the last tail node. Is infinity greater than 36? Yes. So basically I'll come down at L2, right? Then again I'll check at the next node at L2. Is infinity greater than 36? Yes. So I come down. Then again I check at L1 or the next node at L1. Is infinity greater than 36? Yes, it is. Then I'll come down at L0 and I'll look at the next node 40. Is 40 greater than 36? Yes, it is. So I'll come down. But this is the bottommost linked list, or we are actually at L0, so I cannot come down. That means that the search was actually unsuccessful, right? So the search operation is very simple. But if you look at the number of steps that we need to perform in the search operation in a randomized skip list, it is different than the number of steps that we need to perform in a perfect skip list when we do a search operation. How is it different? Because we saw that in a perfect skip list, at most we need to take or we need to do only 2 comparisons. But here, as you can see in this L3 or the topmost level, you are actually doing 3 comparisons. So basically there could be more number of comparisons. Had there been more number of elements over here, if suppose I would have promoted even 20 over here, so there would be 4 comparisons. So what we can derive out of this is that, so in case of a randomized skip list, the time complexity for search, we cannot directly say that it is 2 into number of levels in the skip list. Why? Because we don't know that in a particular level will there be just two comparisons. There can be more number of comparisons as you saw over here, right? So we cannot say this. And at the same time, we cannot say that the number of levels in the skip list are going to be just log n, or approximately they will be equal to log n, because it would have been possible, because as you can see that here we are having n number of nodes, here we are not actually having n by 2 number of nodes, here we are not having n by 4 number of nodes, so we are not following this strategy. So it is not necessary that we will be having at most log n levels. So this case is also actually not deterministic. The number of levels in a skip list can vary, right? If suppose 30 over here was promoted to another level until 10 more levels, so there would be 14 levels for the same skip list with just one element, that is 30, being there from L4 to L14. So basically, in that case, the number of levels would be greater than n. Here n is actually equal to 8, so those number of levels would be greater than n, right? So we cannot say that this value or number of levels in skip list will actually be equal to log n. We cannot even say this, right? So in the next video, we will see that in spite of these two non-deterministic characteristics of a randomized skip list, the search operations time complexity in case of randomized skip list comes out to be order of log n itself with high probability, right? So we will be doing a probability computation in the next video or a better analysis in the next video and find out that this complexity remains as order of log n in spite of these two randomized characteristics. So now let us see how to perform the insert and delete operation in a randomized skip list. So now just look at this skip list. So now I'll be performing the insert operation in this skip list, right? So I've changed the skip list right now and I want to insert a node with value 25, right? So I want to insert this node. So in order to perform the insert operation, first we will look for the position where we have to insert this node. So for looking at the position or finding out the correct position for inserting this node, we need to search for this node. So we need to do the search operation first, right? So we will first search for 25, right? And then we will insert the node, right? So when we search for 25, we start from here. Is 15 greater than 25? No. So we come over here. Is 30 greater than 25? Yes. So we come down. So then at this level we check. Is 20 greater than 25? No. So we come at the right. Is 30 greater than 25? Yes. So we come down. Is 30 greater than 25? Yes. So we come down. And now we are at the bottommost level and we check. Is 30 greater than 25? Yes. So we have to come down, but we are at the bottommost level. That means this is the place where we will be inserting 25, right? So now we have inserted 25 in our skip list, but we have just inserted it at the bottommost level L0. Now we have to take a decision. And what decision we have to take? Do we have to promote this node 25 to the top level or not, right? Because we need to determine that is this node to be promoted at the top level or not. So how we can take this decision? So let us do one thing. Let us toss a coin, right? Let us toss a coin. And of course it's a fair coin, right? And in case of fair coin, you know that the probability of head is 1 by 2 and tail is also 1 by 2. And when we toss a coin, if it comes out to be head, that means we will promote the node to next level, right? And if it comes out to be tail, we will exit, right? So suppose in the first case, when I tossed a coin for the first time, it came out to be head, right? So in that case, what I'll do, I'll promote this node 25 to the next level over here, right? And then again I toss a coin, right? I toss a coin again, and again it came out to be head, right? So again I'll promote this node 25 to L2, right? And suppose again I toss a coin, right? I toss a coin for the third time, and this time I get a tail. So when I get a tail, what I do is that I exit. That means my insertion of 25 is completed, right? So basically here, as you can see, we are tossing the coins until and unless we are not getting a tail, right? So here we will have a while loop, right? Until and unless we are not getting a tail. Now you might say that we need to add another condition in this while loop, that until and unless we are not reaching the last level. But that condition is not required, because suppose if I had tossed the coin for the third time and again I would have got head, right? So what I'll do, I'll actually promote this node again to the top level, right? And suppose again I get head for the fourth time. So it doesn't matter that this is my last level. I'll have another level at the top. I'll make another level at the top, and I'll promote this node over here. So that will be my L4, right? And here I'll drop the head node, and here, so here again I'll have a tail node, and this node will be pointing to that tail node, right? And again if I get a head, and like in this way I get a head for suppose another 10 number of times. So suppose even when I talk about the 10th time, if I get ahead, right? Until the 10th time, so 5th, 6th, 7th and 8th, so until 10th time if I get ahead, so basically I'll be having the skip list until L10, and from L4 to L10 each of the linked list will be having just one node, that is 25, and finally at L11 when I get a tail, I'll say that the insertion of 25 is completed. So this is how we do insertion in a skip list, or you can also call this a randomized skip list. Now maybe you are getting a glimpse of why skip list is a probabilistic data structure, because we are associating a probability of whether a node has to be promoted to the next level or not. And the reason why we have taken this probability as 1 by 2 is because at the end we somehow want to replicate the perfect skip list. And in case of a perfect skip list, we know that at the bottommost level we have n nodes, and then we have got n by 2, then n by 4 and then n by 8. Right? So basically whatever number of nodes we have over here, half the number of nodes we want at the next level. Right? So what we are trying to achieve is that we are trying to achieve that the expected number of levels even in our randomized skip list like this should be order of log n. That is why we are taking this probability as 1 by 2 and 1 by 2. Right? So now let us see how to perform the delete operation. So suppose if I want to delete the node 20 from the skip list. So again I'll search for 20, right? And then I will delete it at all levels, right? Because the node 20, it is possible that it could be on more than one level. So I delete all the occurrences, right? So first of all, let me search for 20. So I start from here. Is 25 greater than 20? Yes. So I come down. Is 15 greater than 20? No. So I'm at 15. Is 25 greater than 20? No. So I come down. So basically, in this way, I'll find 20 over here, right? And you can actually write your code in such a way that you can also find 20 over here and delete all these three occurrences of 20. Or you can write your code in such a way that you can find your 20 over here, right? So now I'll delete all these three nodes from here. Basically, I'll be changing some of the previous and next pointers, and that is how all these occurrences of 20 will get deleted, right? Right? So that is how we do the delete operation. Again, the delete operation involves the search operation, and then we delete that particular node from all the levels, right? But I want that some questions should arise in your mind. That when we are inserting a particular element, like when we inserted this element 25, and when we said that we will actually be tossing a coin and then determining that if this element has to be promoted to the next level or not. So if suppose we get 100 continuous heads, right, without a tail. Okay, if we get 100 continuous heads, that means we will be having 100 levels with just a single node. So in that case, how we can say that the expected number of levels will be order of log n with high probability? How we can say that, right? So this is the first question that should arrive in your mind, because the result of tossing a coin is not in our hands. It can actually lead to 100 heads without even a single tail, right? So the first question is, can we have infinite number of levels in skip list? Or can we actually say that having infinite number of levels in a skip list is something very feasible, right? Or how can we actually prove that the expected number of levels in a skip list will always be order of log n with high probability? The second question that should arise in your mind is that when we are searching for an element in such kind of a randomized skip list that is not having a very proper structure, so in such a case we are actually performing a lot of steps, right? And as I said earlier, it is not necessary that at each and every level we are comparing just two nodes or at most two nodes. We might be comparing even n nodes at a linked list, if that can also be a possibility. So how do we ensure that the time complexity for the search operation remains as order of log n? So how do we ensure this? That in spite of having this randomized structure of a skip list, the time complexity for the search operation will be order of log n with a very high probability. There will be a very high probability that your time complexity will be order of log n when you search for any element in this randomized skip list. The third question that should arrive in your mind is that we actually started learning this data structure skip list because it was providing us a time complexity lesser than order of n that we got when we search for an element in a sorted linked list. But at the same time, this data structure skip list seems to be having a higher space complexity, or all these nodes are actually redundant when you talk about a skip list. And in case of a linked list, you are just having n number of nodes. So what is actually the trade-off when we look for a better time complexity? How much are we compromising in case of a space complexity? So the third thing that we need to answer is that what is the space complexity of a skip list? So all these three questions or all these 3 points, I'll be proving them with an in-depth analysis in the next video. So in this video, we saw that why do we need a skip list? What is a skip list? When do we call a skip list as a perfect skip list? And why a perfect skip list is not ideal in real life, and that is what took us to a randomized skip list. We saw the search, insert and delete operations in the randomized skip list, and we are left with these 3 points that we are going to address in the next video with an in-depth analysis of this data structure skip list. Now let us meet in the next video where we will complete this data structure skip list by doing a probabilistic and an in-depth analysis in order to address these 3 points. That's all for this video. See you in the next video. If you liked my video, please share it as much as possible and do subscribe my channel because I'm going to upload many such videos in the upcoming days.